In the previous lecture, we have started to discuss the quantum theory of paramagnetism. Actually, I have told you in that lecture that the complete quantum theory will be dealt in two parts of the lecture. We have already seen the first part of quantum theory of paramagnetism, and today we are going to see its second part. Actually, in first part of the theory, quantum theory on paramagnetism, you have seen that how we can calculate the magnetization and the magnetic susceptibility, particularly under the condition when temperature is very high and field is weak. So in this case, when temperature is high and field is weak, we have already discussed the magnetic susceptibility in our first part of the lecture on this quantum theory of paramagnetism. Now actually today our aim is to see its calculation just in reverse condition, that today we will see how we can calculate the magnetization of a paramagnetic gas when temperature is low and field is strong. Okay. So this is the subject matter of today's lecture. Definitely when you will be asked this question that discuss the quantum theory of paramagnetism, you have to write the answer combining both of these parts. I have divided this lecture in two parts, but answer will be written in actually the combination of this first and second part. Okay. So definitely, as this is just the subsequent lecture or just another part of the first lecture, so definitely you have to start with the basic equation which you have seen in our first part of lecture. Actually, you have seen that the magnetization M of a paramagnetic gas is defined like this. I have discussed this result in very detail in our first part of the lecture. How this result takes place, I have already discussed. So here I have directly mentioned it. M is given as Ng mu b times summation over Mj from minus j to plus j, Mj times exponential to the power Mj g mu b times h over kBt, and divided by summation over Mj, where Mj runs again from minus j to plus j, and exponential raised to the power Mj g mu b h over kBt. This was actually the starting equation, our first equation, our basic equation, and we have actually simplified this result under the particular condition of high temperature and low field. Okay. But today we will see the simplification of this result when temperature will be low and field will be strong. Okay. I hope as you have watched the first part of the lecture, so definitely you have an idea of the terms used in this equation. You can see what is this M? You know this is magnetization, and when you say magnetization, that means the magnetic moment per unit volume. Okay. And what is this N? You know this N is the number of atoms or molecules, or you can say this is the number of atomic or molecular dipoles per unit volume. Okay. Because the paramagnetic gas, the molecules of a paramagnetic gas has already permanent dipole moment. Okay. And G stands for Lenz's splitting factor, you know, and mu b is the well-known Bohr magneton, and H is the external magnetizing field in which our specimen is placed to magnetize it. Okay. And this Kb is a universal constant, you know, this is called Boltzmann constant. Okay. Now, as I have told you that in the in this equation actually you can see, you have learnt in the first part of the lecture that this mj g mu b, this is actually component of magnetic moment parallel to h. Okay, this if h is directed in this direction, then the component of magnetic moment in this direction is given by mj times g times mu b. Okay. Now, as I have told you that in our first case we have discussed the situation T high and H small, that is mj g mu b over h mu b h over kbt is much smaller than 1. In this situation, what is the value of m, what is the value of chi, we have already discussed in our first part of the lecture. Okay, so I have mentioned that already discussed in part 1. Okay, so now in today's lecture we are going to see the just reverse situation. You can see in first part of the lecture we have considered temperature is high and field is small. Now we are considering temperature is low but field is high, that is field is very strong. So in this condition, what will happen? In this condition, this number mj g mu b h over kbt, can you say that this will be smaller than 1? Definitely not. Definitely not. Because h is actually larger here and t is smaller. So definitely this will be not less than 1. Actually, in the first part of the lecture you have seen that we have expanded the exponential term e to the power, although that was not e to the power x. You can see there is e to the power mj g mu b h over kbt, and if you suppose that that is equal to x, then we have written that this e to the power x is equal to 1 plus x in first approximation, because in the first case we have seen that x is much less than 1. But can you expand this exponential factor in this series? In present case, answer will be definitely not. Because in this case, the power of the exponential, which is mj g mu b h over kbt, that is not less than 1. So you can't take such an approximation. Okay. So in this case, actually exponential factor will be taken at each. As it exists in this basic equation, we will not alter it. Okay. So let us see what will be then the magnetization when we will simplify this result. Actually, for simplifying this result, let us consider that this factor g mu b h over kbt, it means except mj, the remaining factor g mu b h over kbt, for simplicity we consider it is equal to x. Okay. So when you will assume that g mu b h over kbt is equal to x, then what will be this equation A in terms of x? You can easily write it. Here you can see there will be e to the power mj times x, and in denominator 2 the power of exponential will be mj times x, because g mu b h over kbt has been assumed to be equal to x. Okay. So let us see. In accordance with that result which we have learnt in previous lecture, m is given as n times g mu b times summation mj running from minus j to plus j, mj times e to the power mjx, and divided by summation mj running from minus j to plus j and e to the power mjx. Okay, e to the power mjx. Now you can see This expression, that is mj times e to the power mjx divided by this much. Okay? This can be written as d dx log summation mj from minus j to plus j e to the power mjx. You can actually differentiate it, and you will see after differentiation your result is this much. Because you know, derivative of log of this much will be 1 over e to the power mjx, which is the factor in denominator. And then we will differentiate this e to the power mjx. That will be equal to mj times e to the power mjx. So you can see, you can check that this d dx operated on log summation over mj from minus j to j e to the power mjx, that is simply equal to this much. Okay? This is very, very simple differentiation. Okay? Now expand this series. Since j runs from minus j to plus j, so at a step of 1, you know, so this result can be written as n g mu b d dx log, and for this summation, for this series, you can write this. Actually, I have started for writing the terms taking j equal to plus j first, and then we will take the other values of j at a step of decreasing one. Okay? So the first term will be e to the power jx, second term will be e to the power j minus 1 into x, the third term will be e to the power j minus 2 into x, and so on. And finally, the last term will be e to the power minus jx. Can you say how much is the number of terms in this series? Definitely you can say. In first part of the lecture we have seen that for a given value of j, the quantum number mj has total 2j plus 1 values running from plus j to minus j at a step of 1. Okay? So the total number of terms in this series is 2j plus 1. Okay? And you can see, actually this series is in geometric progression. Okay? Containing this 2j plus 1 terms. I have written it here. It is a GP, geometric progression, with 2j plus 1 terms. And what is the common ratio? Common ratio is e to the power minus x. You can check. The second term is e to the power j minus 1 into x, and first term is e to the power x. Okay? E to the power x. First term e to the power not x, but e to the power jx. So you can see this is e to the power jx times e to the power minus x divided by e to the power jx. Now this will cancel out, and the result is e to the power minus x. So what is this e to the power minus x? This is common ratio. Okay? So number of terms is 2j plus 1. First term is e to the power jx, and common ratio is e to the power minus x. And you know, the sum of this series, which is in geometric progression, a plus ar square plus so on plus ar to the power n. Okay? What is the sum of this series? You know, this is a times 1 minus r to the power n divided by 1 minus r. Here r is the common ratio. So apply this formula for the sum of geometric progression to evaluate the sum of this series. You can see. So this will be ng mu b d dx log. This is at is. And for this series, I am writing here a. For a, we will write e to the power jx and 1 minus r to the power n. R is e to the power minus x, and at the place of n there is 2j plus 1, because in this series the number of terms is 2j plus 1. So this will be 1 minus e to the power minus 2j plus 1 times x, and divided by 1 minus r. R is e to the power minus x. Okay. So I think you have clearly understand how we can replace this series by these terms using the formula of geometric progression. Okay. Now, after getting this result, we will simplify it to some extent. And for this, let us multiply the numerator of this sum and the denominator of this sum also by a factor e to the power x over 2. Actually, this step you have to remember. To cast this equation in a convenient form, it is necessary that we have to multiply the numerator and denominator both by this factor e to the power x by 2. Then this equation will be in a suitable form. Okay. So you can see in this condition m will be n g mu b d dx log, and this numerator will be multiplied by e to the power x by 2, and this denominator will be also multiplied by e to the power x by 2. You can do the algebra. I am not talking about term to term. This is a simple fact. And so you can see the terms inside this logarithm will become e to the power j plus half times x minus e to the power minus j plus half times x over e to the power x by 2 minus e to the power minus x by 2. But you know, e to the power theta minus e to the power minus theta divided by 2, this is equal to what? This is sine hyperbolic theta. So e to the power theta minus e to the power minus theta, this is 2 sine hyperbolic theta. So using this formula, can you say what is this e to the power j plus half x minus e to the power minus j plus half x? This will be simply 2 sine hyperbolic j plus half x. Okay. And in denominator, you can see this factor will be equal to 2 sine hyperbolic x by 2. 2 and 2 will cancel out, and so your result is this much. You can see this is ng mu b d dx log sine hyperbolic j plus half x divided by sine hyperbolic half x. Okay. Now actually we will differentiate this function log of sine hyperbolic j plus half times x over sine hyperbolic half x. I have not done each and every step of this differentiation. You can do it. Log this much should be differentiated with respect to x. And you will see when you will do the algebra, after differentiation, our result will become a simpler result like this. M is equal to ng mu b j times 2j plus 1 over 2 cot hyperbolic 2j plus 1 over 2j times a minus 1 over 2j times cot hyperbolic a divided by 2j. Actually here I have written this factor a instead of j times x. For j times x, a has been written. But you can see x, we have assumed in the beginning that x is equal to g mu b h over kbt. So actually this a has been written for j g mu b h over kbt. Okay. Now let us see this result. Actually in this result, this n times g mu b j, this is the maximum value of this magnetization, because the maximum value of the factor inside this square bracket will be equal to 1, and then m will be maximum, and that maximum value will be equal to Ng mu Bj. In fact, this Ng mu Bj is also called saturation magnetization, okay, and it is denoted by Ms. So you can see that result has been written as m equal to Ms times this much, Ms times that much, okay. In fact, I have written, you can see the maximum value of magnetic moment m represented by Ms will be equal to Ngjj mu b. It means Ms is equal to Ngjj mu b, and this is called saturation magnetization. Why it is called saturation magnetization? You have also learned this in the classical theory. Actually, a situation comes when field is very strong, then almost all the atomic or molecular dipoles align themselves on the line of the magnetizing field. So magnetization is completed. After that, if you will increase the magnetic field, there will be no increment of magnetic moment, because all the magnetic moments now you consider that they are aligned along the magnetic field. So after this situation, magnetization becomes constant, and that constant magnetization or maximum magnetization is called saturation magnetization, and that is denoted by the symbol Ms. Okay. So m in general is now given as Ms times this factor inside this square bracket. Now actually the ratio of m and Ms is denoted by the symbol B of A, where B of A is known as Brillouin function. This is called Brillouin function. Okay. Now you know the least value of quantum number J is half. You know J is the total quantum number, and this is L plus minus S. Okay. But when you will take the least value of L, that is L is equal to 0, then J is equal to only half, because S is always equal to half. And in this case you can't take minus sign, except L equal to 0. If L is equal to 1, L is equal to 2, then you can take both the plus minus sign. But when L is 0, then you have to take only J equal to L plus S. It means J is equal to S, and that is equal to 1 by 2. Okay. So this is the least value of J. And when J is equal to 1 by 2, okay, J is equal to 1 by 2, then you can simplify this result defined in equation C, that this B of A, which is Brillouin function, and that is equal to m over Ms. What will be that? You have to put J equal to 1 in the terms inside this square bracket, and after simplification you will see that when J is half, then the Brillouin function defined in this square bracket will become tan hyperbolic A. And when you will expand it, this will be A minus A cube over 3 plus so on. Okay. And this is the value of this Brillouin function when J is equal to half, that is you have taken the least value of J. But now take the largest or the highest value of J, and what is that value? That will be infinity. When you will take J equal to infinity in this expression for BA, then you will see that this BA is equal to cot hyperbolic A minus 1 over A. You will get it after substituting infinity for J. After observing this result, can you remember what you have learnt in Langevin theory of paramagnetism? Definitely you can remember. This cot hyperbolic A minus 1 over A, this is nothing, this is simply the Langevin function. So actually when J is maximum, that is J is infinity, then this Brillouin function is just identical to the Langevin function. Okay, this is a very remarkable fact. In general, Brillouin function is different from Langevin function, but when j is equal to infinity, then Brillouin function is equal to Langevin function. Okay. So in this way, we have obtained the value of magnetization, and once you know the value of magnetization, dividing the value of magnetization by the magnetizing field H, we can get the value of magnetic susceptibility chi. Okay, you can do it. Now let us see this result for magnetization M or this result which is defined in B, both are same. Actually, it is found that the result B and C is in good agreement with the experimental result in comparison to the results obtained from classical theory. The result for the magnetization and susceptibility obtained by classical theory slightly deviates from the experimental value, but this result obtained in this case by the quantum mechanical theory actually agrees very well with the experimental result. So quantum theory is superior than the classical theory. Okay. So in this way we have completed our complete lecture on quantum theory of paramagnetism, and in examination whenever you have to ask this, you will be asked this question, you have to write down the answer of both of writing the matter in both parts of this lecture. Okay, thank you very much.